Here's a diagram showing the footprint of the blankets prior to installation at WBC 715, and these mark the location of the mini point rosettes. Looking at the plots here, we have depth in centimeters plotted against the analyte concentration in milligrams per liter. The blue is bromide, red fluoride, the yellow is nitrate, and the purple is sulfate. So the purpose of doing these vertical profiles prior to installation of the blankets was to determine if there was any natural high fluid flow occurring in the location prior to putting in these devices. The right side shows that the groundwater concentration for fluoride, bromide, and sulfate are not very different from the stream water concentration. So even if there were some hyperic flow in that location, we couldn't really say. On the left-hand side, we can see that the groundwater concentration and stream water concentration are clearly different, but there is no penetration of stream water at least to 3 centimeters depth, because these are very consistent with that for all the analytes there. In the center location, though, we do see that there might be an indication of hyperic flow. The strongest indication of that is nitrate, but we understand that that is being transformed in the subsurface, and we can't say that this is strictly hyperic flow because it could be that there's some biogeochemical activity going on there. Whereas the fluoride is a conservative tracer, and it clearly shows a little bit of a dip, suggesting that there is some hyperic flow here in the center of the stream to 3 to 5 centimeters depth. So now if we install the blankets and we have the benefit of having this high concentration of bromide in the stream, the mini point samples from above and below the blankets clearly show that there is some hyperic flow. On the right-hand side, above the blanket, we're seeing a penetration to roughly 3 centimeters, where on the downstream side, we're seeing something between 7 and 10 centimeters of hyperic flow penetration. And since we couldn't really tell if there was any hyperic flow prior to the installation of the blankets, we're not sure if this is induced hyperic flow, but we suggest that it's not induced, but rather there was natural hyperic flow and is amplified slightly by a few centimeters depth. Looking at the center blanket upstream, again showing some hyperic flow to a few centimeters depth, but looking at the downstream profile, it's not definitive whether there's some hyperic flow or not. There's a very slight bump in concentration in the bromide at 3 and 7 centimeters depth, but it's well below the stream concentration, suggesting that there might be a little bit of penetration of hyperic flow, but it's pretty limited. So it seems that the blanket is blocking hyperic flow in this case because there was natural hyperic flow occurring before the installation. So looking at the full analyte suite from the center upstream location, this is after the blankets, and this is prior to the blankets overlaying. So from this, we can see that the analyte concentration is not changing significantly with depth, which we interpret as that the blankets have not significantly changed hyperic flow in that location. So these blankets are collecting stream water and groundwater. It seems that hyperic flow is likely the culprit of that stream water entering the blankets. But we made some interesting observations during the July campaign that there were snails coming up under the blankets, suggesting they were starved for oxygen. So we were curious of what was going on underneath the blankets. So in March 2013, we deployed passive diffusion samplers buried in the stream bottom, shown in this diagram here. These samplers were buried prior to installation of the blanket, were left in for the full 3-day period, and then retrieved after removal of the blanket. It's important to note that these are passive samplers, so they are not affecting any of the surrounding water flows during their sampling period. The plot here shows the depth below the stream in centimeters and the isotopic helium ratio, R over RA, showing that for the right, center, and left diffusion sampler profiles, there's clearly a different signature of groundwater from the stream water, and that these samplers are effectively isolated from the stream water underneath the blankets. The single mini points samples that were collected underneath the blanket show consistent analyte concentrations between 10 and 20 centimeters depth, suggesting that there is not a deeper hyperic flow path going underneath the blanket. So it kind of brings us to, what are these blankets really good for? They can't measure groundwater. It's getting some mixture of stream water and groundwater, and they're not really a great measure of discharge. So if we look at the sample results from dissolved gas, showing the concentration in milligrams per liter for the various constituents of reactive gases and noble gases, from the blankets marked in blue and the Darcian point measurement marked in red, we can see a systematic reduction in, or decrease in concentration of the reactive gases from depth to the sediment water interface, suggesting that we are capturing some of the subsurface reactivity with the blankets, whereas the noble gases show very consistent concentrations from depth to the blankets. So there's not any physical process that is causing the change in the reactive gas concentrations, but rather a chemical one. This is further corroborated with the SF6 samples collected from the blankets and points. The information of interest is here, showing that once we've corrected for the presence of stream water in the blankets, the apparent recharge years from the SF6 are agreeing quite well between the blankets and the points. So in conclusion, discharge measurements are variable for the blankets. The samples collected from the blankets show that they are capturing a mixture of groundwater and surface water, but that they are capturing representative groundwater once you've corrected for the presence of stream water. And the vertical profiles in the stream bottom show that blankets are altering hyperic flow, but not as we expected. They're not creating a lot of hyperic flow, but blocking or slightly amplifying natural hyperic flow. This suggests that you could use the blankets to manipulate this to the investigator's advantage. So, overall summary, for the Shelby tubes, they are an effective direct measure of specific discharge and hydraulic conductivity, and importantly, that's measured in the same sediment. The Shelby tubes are poorly suited to measure low gradients, but that's common with all hydraulic methods, and it is a discrete location measurement. The seepage blankets are capturing representative groundwater and in a spatially integrated and flow-weighted manner, which is useful for sampling of the age tracers. The blankets are capturing the sediment-water interface exchange, and they are altering some hyperic flow, while discharge measurements are variable. So I'd like to acknowledge Dr. Solomon. He's been really fantastic to work with. I can't express enough gratitude for Kip. My committee members, Paul and Vic, thank you for agreeing to sit on my committee. Our North Carolina State collaborators who are working on this larger NSF project, Troy Gilmore, Dr. Genero, Matt Burnett, Scott Becker, and others. Our USGS colleagues that helped in the field or in the lab, Donald Rosenberry out of Denver, and Brian Kimball, and also the North Carolina Water Science Center employees that helped us a lot in March 2013. I'd like to give my thanks to the U of U Dissolved Gas Lab, Alan, Will, and Olivia. They were helpful with manufacture, with analysts, with moral support. They've been really great. Thanks to the department for having such a beautiful building, having a machine shop that I could make use of, and the very useful discussions that I've had with everybody. Thanks to the National Science Foundation for providing funding, and to my family and friends, my parents who made it here, who've been lovely and supportive and really important to me, and to my partner Britt, who's just been nothing but the best ever. So with that, I'll take any questions.
So, yeah, we'll just open it up to questions from either the committee or anyone in the audience here for a little bit.
I have a question.
Sure, Britt.
The location, you touched on it a little bit, but what is the significance of that area in North Carolina? Why has there been so much interest in there?
Yeah, so that kind of gets back at the larger project goals of the NSF, is that we're looking at nutrient loading into the streams, whereas terrestrial application has been reduced for 10 to 15 years now, but we're still seeing a lot of this coming into the streams. So we're trying to understand better how much longer can we expect there to be a lot of nutrients coming in by trying to understand the residence time of the groundwater.
The nitrogen fertilizers that are used in the coastal plain for growing tobacco and lots of other crops then create massive nutrient loadings in the estuaries where those streams discharge into the ocean, causing algae to bloom and lots of sort of unfavorable aquatic conditions. So North Carolina has been really vigilant at trying to lower those nitrogen loadings, but it comes at the detriment of the farmers who, the more fertilizer you put on, the more your yields, and yet, it's a balance between these two things. And this has been a major headache for them because for 10 years, the farmers have cut back massively on their use of fertilizers, and yet it hasn't helped yet. The streams haven't, their nitrogen content has not lowered, and so that's kind of the basis for this.
Sure.
Yeah. Kind observation brings up maybe a suggestion that needs to do something about solubility of nitrates in the root environment. Am I saying if they absorb these nitrates, we wouldn't be seeing them in the river? Is that so?
That's a complicated issue.
I mean, ideally, one would like to put on just the right amount of fertilizer to have it 100% taken up by the plant.
Absolutely.
I think everyone would probably like to do that. How you accomplish that in an optimal sense and still get, it's like your lawn, the tendency is to put it on in excess.
Absolutely, yeah.
And let the, like many of us, give us as much as we'll eat, and try to let us self-regulate, which we don't do so well.
Yeah, okay.
Can you go back to your bromide tracer slide the first time you introduced it?
Sure. You're talking about the arrival in the blankets here?
Uh-oh.
It's pretty quick. But what was your question?
Well, there you have the figure of the time for when bromide, there you go, was introduced into the blankets and then in the stream, and I'm just curious, so it starts at 16 minutes and 25 seconds, is that correct?
Oh, sorry, that would be military time,
Oh.
4:25
Okay.
in the afternoon.
So, I'm just wondering, you're measuring the 715 meters downstream from where you injected the bromide, right?
Mhm.
So, I was just curious to know how long it actually took for the bromide to get from the injection site down.
Our, I don't have the start of the injection time off the top of my head, but our back of the envelope calculations for the full 2,700 meters was about 4 hours.
Okay.
So to get from the injection site to 700 meters was probably a little less than 2 hours.
Okay.
Yeah.
We talked about the variability of blankets between measurements. I'm
Mhm.
wondering how much seasonality may impact that since you're in March and dead of heat in July.
Yeah, that's a good point. We did see varying stream discharge during that time, but we're not really comparing the blanket measurements in May to the blanket measurements in July, but rather the May measurements from blankets and Darcian to each other. So there's less of a temporal component of that. So we're really comparing this blue blanket measured specific discharge to this Darcian
Okay.
for that time period.
That's the slide I was going to ask you about.
Okay.
Very nice, lots of work, great. How did you do the Darcian? I'm not sure
Darcian,
exactly how you.
yeah, Darcian was completed by our North Carolina State collaborators. And the vertical hydraulic gradient is measured with a light oil piezometer. And the hydraulic conductivity is measured with the falling head permeability test.
Okay.
Yeah.
And so, yeah, all right. I was wondering how you got the hydraulic conductivity and what you were using. And then, and is this from, is this a number of piezometers right there where that
It is.
transect of the blanket is, or just a single one, or?
Yeah, so this is for the July campaign. This is actually the mean specific discharge from the blankets deployed at 3 separate transects.
So like 9 blankets or something?
Like 15.
Yeah.
Yeah. And for the Darcian measurement, it's something close to 50 measurements.
So 50 piezometers.
So they, did 5 measurements at a time across a transect and then moved upstream.
Yeah.
For the March comparison, the blankets were deployed at 1 transect, but we took 5 measurements over a period of 3 days. And the Darcian is from 1 transect of 5. So the reach mass balance calculations are, the discharge from reach mass balance is from the start of the point in blanket reach to the end of the point in blanket reach. So that's the average specific discharge over that few hundred meters of stream reach.
Based on the dilution of the bromide.
Correct.
And then the flow tracker.
Yes.
That's the same deal.
Yeah, the same concept. We measure the stream discharge at the top of the reach and at the bottom of the reach, and because there's no obvious surface inflows, we take the difference in those 2 discharges to be gained from groundwater.
From that little smaller, that red stippled reach you had in your first figure.
Correct.
Yeah, even with 50, you probably get more integration maybe with the blankets. I don't know.
Yeah, that's, Kip and I have been talking about it, and these results, suggest that the blankets are not really sampling all the spatial variability. What it suggests is that the correlation length is larger than the size of the blankets, so we're really just collecting a snapshot rather than the entire variability that's in the stream.
Well, I was kind of wondering if you didn't get more, still even despite that the blankets were doing more of an integrating than even 50 Darcy or well points.
Yeah,
I don't know, but
that's a good question. Our our feeling is that since the Darcy measurements are in fairly good agreement with the reach mass balance, that, you know, the reach mass balance is really kind of the golden, yeah, that's really the go-to. So it suggests that it really are the blankets that are the outliers rather than the point measurements.
Yeah. Yeah, that's a good point, that those two in the middle are probably, well, or the reach mass balance is probably maybe the thing that the other one should be.
Yeah.
Yeah.
So kind of the question is how many blanket transects do we need to measure discharge on to get a representative specific discharge? You know, and that's something that's worth exploring. Measurement of 50 points is labor intensive.
Yeah.
You know, the blankets are a little difficult to install and move around, but once they're in place, you can leave them there for a number of days and take continuous discharge measurements off of them. So.
And then there's still that flow tracker that it comes
Yeah.
out at double, that's.
Yeah, this flow tracker measurement is actually over a considerable portion of the reach. I believe it's from 200 meters downstream to 800 meters downstream during March.
So it's larger than the other?
It is larger.
Oh, okay.
Yeah, so it's capturing a bigger portion of the
Yeah.
reach.
Then it would, yeah.
But it's still normalized. I mean, if there were a constant groundwater inflow over that larger reach, it should
Yeah.
still be the same number.
So it is normalized
Yeah, it's
over
all
length.
Yeah, these are meters per day, not
Right.
total discharge.
Yeah.
But it's the largest, by far the largest scale measurement
Yeah.
that's up there.
And it doesn't agree with the reach mass balance.
No, but the reach mass balance, particularly in March 2013, was fraught with difficulties. We didn't really get the concentration of bromide in the stream as high as we would liked it to. So the dilution as is going downstream was very subtle and was really testing our analytical capabilities.
Okay, yeah.
It also, of course, just depends on your what you mean by agreement. Because all of us that make flow measurements of anything know that,
Yeah.
you know,
0.3 and 0.65 are pretty close.
Do you have high water in March? Is that what's up? Is that why the bromides didn't get the job done?
Yes, we did have a larger stream discharge. There was more water in the stream.
Yeah.
And we also suffered the misfortune of having a pretty large rain event right
There you
before
go.
we got there in March. So we were on the falling limb.
Yeah.
So yeah, there was a lot more stream water than we anticipated.
And John, thanks for studying.
Oh yeah. You're welcome.
That was an inside joke to what we had on our drive around Colorado.
Yeah, that's right. That's right.
are there any other questions from anyone at this point? If not, maybe join me once again in thanking John for his We'll take a very short break, as in 2 or 3 minutes. If any of you need to leave, feel free, and then we'll reconvene and have some more specific questions from the committee. I'll have some diet.
Yeah, there you
How did you do? I'm sitting down because my butt's a little tired. Thank you. Are you in the department? Is that the idea?
Yeah, man.
No, I work in the U.S. Senate.
Ah.
Thank you. Thank you for coming. Yeah, sounds good. Okay, you were able to follow it?
Well,